Win free airtime with hashtag LearnOn1. Share your comments on the lessons. WhatsApp your feedback, name and town to 081 200 6659. Hashtag LearnOn1. Invite learning in.
To Unit 3. There we go. Unit 3, the heading is Isotopes. Who can give me the definition of an isotope? Yes. Atoms of the same element, in other words, they've got the same number of protons, but they've got different mass numbers, which means the number of neutrons. When they ask the definition for isotopes in a test or an exam paper, we had specimen papers, they give isotopes 2 marks. So when we were discussing it, everybody gives the definition of an isotope: atoms of the same element having different numbers of neutrons. 100% correct, 1 mark. Because they want you to explain atoms of the same element have the same number of protons. Alright? So isotopes, atoms with the same number of protons, same atomic number, so please state it like that, having different mass numbers, which means the number of neutrons differ. Otherwise you're going to lose 1 mark. Alright. Okay, the definition of an isotope. Atoms of the same element. Let's do this in a different color. Atoms of the same element, in other words, they've got the same number of protons. There we have it, same number of protons, but they've got different numbers of neutrons, in other words, different mass numbers. Please, especially if you see the definition counts 2 marks, explain atomic number and mass number. Do you understand? Okay. Now, we've done isotopes in grade 8, grade 9. And this year we have to go one little step further. Now, some isotopes are unstable. The reason being is the unstable isotopes often have more neutrons than the stable one. It's as if the nucleus becomes too large and it makes it slightly unstable. Now, when we get unstable isotopes, we find very often that they give off energy in the form of radiation. All right? Uranium-238, isotope 238. Remember, uranium has got 92 protons. The mass number is 238. But there's a 234 and a 235 isotope as well. But the 238 one is especially unstable. Now, in an effort to become more stable, this nucleus gives off some energy. We call that energy radiation, and we talk about they are unstable, so they tend to decay, all right, break down or change by giving out energy. Now, radioactive decay, not all elements undergo radioactive decay. For example, carbon. Carbon has got 2 very common isotopes, carbon-12 and carbon-14. Carbon-12, how many electrons does carbon have? 6, it's atomic number 6. So carbon-12 will have 6 protons, 6 neutrons. But carbon-14 will have 6 protons and 8 neutrons. This makes carbon-14 unstable, and carbon-14 is radioactive. All right. When something undergoes radioactive decay, also known then as nuclear decay or radioactivity or nuclear radiation, it's just different terms referring to the same basic thing. It is the process whereby an unstable atomic nucleus, for example, a uranium-238 or a carbon-14, okay, is going to give off energy. What must you remember? Where does this energy come from? The nucleus. Okay. Normally, if I take a piece of wood, I throw it on the fire to burn, where does the energy come from? If I take a piece of wood, and I put it on a fire, and I burn it, where does the energy come from? What's the store of chemical potential energy? Where is it stored? In the bonds. Okay? Remember, wood is a hydrocarbon fuel, so it consists of carbons bonded onto each other covalently and hydrogens bonded onto the carbons. When I burn wood, I break the carbon-carbon and carbon-hydrogen bonds. Okay, it's a chemical bond that is broken. But from radiation or radioactive decay, the energy does not come from making or breaking chemical bonds. It comes directly from the nucleus. All right, the nucleus is unstable, and in an effort to become more stable, it gives off energy. All right. So it emits radioactive particles. There's the next thing. By emitting radiation, and the radiation is an alpha particle, a beta particle, or gamma radiation. Now what happens is, an alpha particle, at this point you don't need to specifically know what an alpha particle is, but an alpha particle consists of 2 protons and 2 neutrons. So it's a fairly large particle, 2 protons and 2 neutrons sticking to each other, and it's shot out from the nucleus. A beta particle is actually an electron that is shot out from the nucleus. Okay, now where do we get electrons? Around the nucleus. So where does an electron come that is shot out from the nucleus? A neutron forms a proton and an electron, and it's that electron that is shot out. Okay, that's what a beta particle is. Now gamma radiation is not a particle. When a nucleus that is unstable shoots out a particle, there's a hole left. So the other protons and neutrons try and reorder themselves to fill that hole. Okay, they move closer together again. When this happens, a burst of gamma radiation is given off. From where can you won't know about gamma radiation, eh? Okay, gamma radiation is part of the electromagnetic spectrum. It's part of the radiation that enters via the sun. Okay, when we do waves, we'll come back to gamma radiation. But it's very high energy waves that are given off. Okay. 3 types of radioactive decay. Here we have alpha decay. They talk about a helium nucleus. Why? Consists of 2 protons and 2 neutrons. If you look on the periodic table, helium, atomic number is 2, the mass number is 4. Okay, so they say a helium nucleus is split out without the electrons on the outside, no? Okay, normally helium has got 2 protons, 2 neutrons in the nucleus with 2 electrons on the outside. But a helium nucleus is just 2 protons, 2 neutrons, no electrons, no? Okay, so a helium nucleus is shot out. That is known as alpha decay. Consists of 2 protons and 2 neutrons. Beta is an electron that is shot out. And remember I said it's a neutron that breaks up into a proton and an electron, and it's that electron that is shot out. All right? And then gamma radiation, well, we'll have a look at gamma radiation when we do waves. But it's also a form of energy that is given out, although it does not consist of a particle as alpha and beta. It's a nuclear bomb. It depends on what it does, but it can either shoot out alpha, beta, or gamma, or some are only alpha emitters together with gamma, some are only beta emitters together with gamma, and some only emit gamma radiation. It depends on what you've got. Okay. Now you don't need to specifically know which one is an alpha, beta, or a gamma radiator. Okay. If we go and have a look at different isotopes, hydrogen, well-known element, element number 1 on the periodic table. It has an atomic number of 1, and if you're going to have a look at the mass of hydrogen on the periodic table up on the board, it's 1.0079. So we round it off to 1. So this tells us what about hydrogen? It consists of what? 1 proton, probably no neutrons, although the comma 0079 tells me, ooh, there's something else there. Now the mass on the periodic table is the average mass of all the isotopes of an element. In nature, these isotopes will occur in a fixed ratio. It's just a natural phenomenon. All right? The first one, with no neutrons, is 99.999% of them. And very few are these two. Okay, so when we add all the masses together and we work out the average in the ratio in which the isotopes occur, we get a mass of 1.0079. Okay? The first isotope of hydrogen is known as protium. It has 1 proton and how many neutrons? How many neutrons? 0 neutrons. Remember, this number is the number of protons plus the number of neutrons. If the atomic number is 1, there's 1 proton. If the mass number must be 1, then there are 0 neutrons. Then deuterium has got 1 proton and 1 neutron, so the mass is going to be 2. So, you see. And the last one, tritium, has got 1 proton. It has to have 1 proton, it's hydrogen. If it has 2 protons, I no longer have hydrogen, then I've got helium. Okay, so 1 hydrogen, 1 proton there, but 2 neutrons to give me a mass of 3. Do you follow? Okay, people, many elements have isotopes. Here's another example. Carbon, I spoke about carbon a little while ago. 3 isotopes of carbon. When we talk about a specific isotope, I refer to it as carbon 12, carbon 13, carbon 14. What does this refer to? The mass number. Okay, what does this refer to? Which element? Yes, and carbon has got 6 protons. Do you understand? Okay, so it tells me which element I have, but it also tells me specifically which isotope I have. Now, normally when we speak about carbon, we are referring to the average of them all. All right, now, people, carbon 14 is unstable. Now, when you are alive, you eat food. The food contains, among other things, carbon atoms. So while you are alive, you take in a specific ratio, carbon. When you die, you are no longer taking up carbon. All right? So the stable carbon remains. The unstable carbon undergoes a radioactive decay, and it changes into something else, because it's going to emit particles or energy. All right? So when they use carbon dating to determine how old an organism is, they're going to have a look at the ratio of carbon 12 to carbon 14. And they know when an organism is alive, the ratio must be in a specific amount. So when an organism dies, the carbon 14 starts to decay. So it becomes less and less and less and less. And then they can go and have a look at how long it takes to decay, and they can go and reckon, okay, so much of this carbon has decayed, this organism has been dead for so long. Okay. If we go and have a look at isotopes of uranium, well, uranium-234, that's the mass number, protons plus neutrons. Uranium-235, protons plus neutrons. 238, protons plus neutrons. So, if uranium has 92 protons, how many neutrons does the 234 isotope have? Calculate. 234 minus 92 equals 142 neutrons. Is that right? Okay. The next one? 143 neutrons. And the last one? 146 neutrons. All right. You follow? Many elements have isotopes. Some are more well known than others. We won't work with all of the isotopes. These are just a few. What do we use radioactive isotopes for? Carbon dating. I've just explained to you. All right, the ratio of the carbon-14. How has it changed? And then they use that to work out how old the object is, the living organism was. Now, radiotherapy, cobalt-60 is used to radiate cancer cells. Cobalt-60 emits gamma radiation, so it's not a particle, it's a wave. Now, particles, if I want to get a particle to go through something, the experiment we do with diffusion, where we put the filter paper in and the gas particles can diffuse through. Why can the gas particles get through? There are spaces. Do you understand? Now, when I want to shoot a particle into your body, a bigger particle is not going to be able to penetrate as good as a smaller particle. And if I have no particle at all, if it's a wave, I can direct it perfectly to one spot. Okay. So gamma radiation is then used to penetrate certain tumors, cancerous tumors in the body. It destroys the cells immediately in the tumor, all right? And then, well, they hope that you will be able to survive it. There's always some extra damage in the surrounding tissues, all right? It's not perfect. It is definitely more accurate than it was 20 years ago. All right? But there is always some damage to the healthy cells as well. But they try and limit it to as little as possible. Isotopes are used to control the thickness of papers. When paper is made, we have huge rollers that roll it out to a certain thickness. When you buy paper, if you go to Walton's and you say you want to buy paper, you can go and buy from thin photostat paper to thicker qualities of paper. Do you understand what I'm talking about? Yes. Now, in the factory where they manufacture it, there must be a mechanism that they have to measure to determine how thick the paper is. And what they do is, as the rolls of paper go rolling through the machine, above and below the machine they have, for example, an alpha or a beta emitter. If the paper is thin enough, the particle can go through, and the presence of radiation is picked up. If it is too thick, the particle can't get through, and an alarm goes off, the paper is too thick, so they have to roll it out. Thinner, they have to apply more pressure. Do you understand? Okay, rolling out metal tins, sheets of metal, etc. They use radioactive isotopes to tell them it's too thick. You must roll it out thinner, okay, to get a certain thickness. Uranium-235 is the uranium that is used in nuclear power stations. It is the fuel. The uranium emits radiation. That energy is used to heat water. The water boils, it turns to steam. The steam drives a turbine. It generates electricity. I don't know the exact mass, but you can use the energy is very, very large, because the energy from the radioactive isotope is calculated. Energy equals mc squared from Einstein's theory. Okay. Now m is the mass of the particle that is shot out. But even though the mass of the particle is very tiny, this is the speed of light. And the speed of light is 3 times 10 to the power 8 meters per second, so you must square it. Okay, so it's 9 times 10 to the power 16. So even if you have a small mass, there will be loads of energy given off. All right. So uranium fuel is usually loaded into the nuclear power generator once every 5 or 10 years. It depends on how much it generates. Yes, it lasts very, very long. Eventually, the big problem with nuclear fuel is the waste that is left after you've used it to generate electricity. It is still radioactive. And the radioactivity remains for a very long period of time, thousands of years. So it's very difficult to store this stuff safely. All right. To get rid of the radioactive waste, you can't burn it because the radiation then goes up into the air with the smoke. You can't throw it into water because it spreads with the water.
Great combo deal from Choppies. Top Score maize meal 10 kilograms, Buck Pro Fed Cook flour 10 kilograms, Banana Elbow 3 kilograms, Rice King 10 kilograms, Sugar King 5 kilograms, white or brown sugar and Polana 1 kilogram spaghetti for only $499,000,095. Choppies, great value for your money.
In a time of uncertainty, false news, and fear, learn on. While the world scrambles to make new sense, while the experts turn around in circles, trying to find their way back to tomorrow, learn on. When classrooms become empty cathedrals and the trees start to bear answers, learn on. Learn on. Until every parent is a teacher, and every teacher is a mentor. Learn on. Until you cross the boundaries of your mind, until you grow eyes and sprout wings. My friend, learn on. On sidewalks, on the floor, at the neighbors, in the market, in hallways, in churches, under trees, at kitchen tables, in riverbeds. Learning doesn't only happen between four walls. Learning happens in the small space of your enormous, beautiful mind. Start where you are. Use what you have. Learn on one. Invite learning in. We have to start off with Unit 7, the building blocks of matter. It's page 115. At the top, the introduction, everything around us is made up of atoms.
atoms, molecules, and ions are the building blocks of all materials. People, I think in grade 6 or 7 in science, you were taught that matter is anything that has mass and occupies space. All right. Now, when we did the kinetic theory, the first thing on that theory tells us all matter consists of particles. Now, what we are going to have a look at in this module is what are these particles? Now, depending on what we have, we know we get different types of bonds. You've done covalent bonding and you've done ionic bonding. Now, another one that we will be doing soon is metallic bonding. But now, depending on the type of bonding, it depends on what particles make up the substance. We know, for example, if I have a covalently bonded substance, we refer to those particles as molecules. If I have an ionically bonded substance, the particles in a salt we refer to as ions. Okay. So, just in general, the particles that we get are atoms, ions, or molecules. All right. All right. People, just definitions. There's nothing new over here. An element is very simply a pure substance. Now, what's the difference between pure and impure? We've done it in the previous chapter. Pure substances have a fixed melting and boiling point. They have a fixed ratio. They are either elements or compounds. Okay? They are made up out of one type of particle. If it's water, we're referring to the particle is H2O. If it is oxygen, we're referring to the particle is O2. All right. So elements then are pure substances that consist of one kind of atom. Remember, the atoms that we have are found on the periodic table. All right. You'll always be given a periodic table. You must just sort of know how to use it. So one kind of atom, and it cannot be broken down further by chemical means. Technically speaking, we can break an atom down. All right, but then we go to subatomic particles. If I go and break an atom apart, I end up with protons, neutrons, and electrons. Now, if I broke an atom of sodium apart, and I put all the protons in a bucket, and all the neutrons in a bucket, and all the electrons in a bucket, and then I went and took an atom of gold, and I broke it apart, and I took all those protons, and I threw it into the same bucket with the other protons, all the neutrons into the neutron bucket, and the electrons into the electron bucket. If I picked up a proton from the proton bucket, I wouldn't be able to say from which element it came. You understand? So, technically speaking, when we talk about the particles that matter is made up out of, we don't go to subatomic level. All right, so we then say that an element cannot be broken down by chemical means. Okay. All right, so mixtures. Mixtures, people, are impure, meaning it consists of more than one thing. If I want to bake a cake, if I have had someone mix the sugar and the salt in a bag, and I have to bake that cake using that sugar or salt, I wouldn't be able to say how much sugar or how much salt I'm using. It's not going to work. All right, it's not pure. My recipe won't work out. So, mixtures are impure. It consists of two or more kinds of substances. Now, these substances can be elements and elements. All right, it can be elements and compounds, or it can be compounds and compounds. Do you understand? And it is varying amounts in varying quantities. So we say then they are impure, two or more kinds of substances, and they are physically combined. In other words, there are no chemical bonds holding them together. If I take a bag of salt and I mix it with a bag of sugar, I've got a mixture of sugar and salt, but the sugar crystals are still uniquely sugar, and the salt crystals are still uniquely salt. They haven't gone and stuck onto each other by some or other method. All right, they are still separate from each other. There are no chemical bonds. So then we say we can separate them using physical processes. That would be sorting by hand or filtering or dissolving it in a solvent and then filtering the one that doesn't dissolve, etc. Okay, no chemical bonds are involved. Then, as a subheading under mixtures, what is an alloy?